Hey everyone, I hope you're doing well. In today's video, we're going to cover simulating HDL in Vivado. In previous videos, we've covered installation and the basics of creating a project and routing it to an FPGA. In this video, we're going to talk about how we can debug our designs in ways that might save us some time. I'm going to be pulling the basics from the Vivado documentation, so if you'd like to learn more, go check it out. I've thrown the link in the description. Simulation is the process of emulating real design behavior in a software environment. Simulation helps verify the functionality of a design by injecting stimulus and observing the outputs. Simulation is one way of testing our hardware. We can simulate it at various stages, but we're going to focus on behavioral simulation. Behavioral simulation lets you simulate and verify your design prior to any translation made by synthesis or the implementation tools. It's typically done to verify code syntax and to confirm that the code is functioning as intended. Jumping into the code, you can see it's pretty much the same project as last time, except I've added some more switches and LEDs. The lower LEDs are driven by switches in a combinatorial circuit. There's also a sequential circuit that divides our clock down to slowly increase an LED value, which is then written to the top 4 LEDs. Right, let's jump into the simulation. This information comes from Chapter 4 of the documentation. The easiest way to run a simulation in Vivado is just by using the interactive waveform editor. So we've opened up Vivado, and all we're going to do is click here on Simulation and then Behavioral Simulation. This might take a while to load. Down the side we have the Scope and Sources window. Then we have all the objects accessible to us in the simulation, and finally the waveform window. Along the top here we have all these buttons, which gives us the option to restart the simulation, run the simulation indefinitely, step the simulation through a set amount of time using the defined time window, step through our code line by line, and finally restart the simulation if we make any source code changes. Looking at the waveform, we can see our wires and registers. Synthesis tools are complex and often simplify designs, so sometimes you might find that a wire or register doesn't appear. You can use synthesis attributes such as don't touch or keep, but oftentimes the easiest thing to do is create an additional wire, and then you can monitor that wire in the waveform editor. In the waveform window we can see our clock, switches, LEDs, the count value for dividing the clock down, and LED values register, which we write to the top 4 bits of the LED array. A Z indicates high impedance, which is a state where the signal is neither high nor low, but essentially electrically disconnected from the circuit. As an aside, tri-state buffers, which include low, high, and high impedance, are useful when you want to create a signal bus that has multiple masters and slaves. An X just means an undefined or unknown. If we run this test bench for 10 microseconds, we can see that nothing really changes. This is because we don't have a clock signal. We can solve this by forcing a clock value as follows. Right-click on the clock, select Force Clock, and then set the leading edge to 1 and the trailing edge to 0. There are other things you can adjust, such as the period or duty cycle, but you don't need to worry about that unless your simulation is dependent on time. By running the simulation, we've noticed our first problem. The count value isn't increasing. Let's go back to the code and see why. Right-click on the signal and select Go to Source Code. And here we can see we haven't initialized a value to the counter. So because our simulation doesn't know what the starting value is, it can't add 1. Let's set the initial value to 0. Save the file, and go back to our simulation and restart it. Now we can see there is an initial value on the count, but of course we need a clock, so let's do that quickly. And if we run it again, we can see the count value increasing. We can see it's increasing, but it's in hexadecimal. So to fix that, just right-click on the signal, select radix, and choose your preferred radix. However, back in our simulation, we can see that LED is still unknown. We know that the LED output register is dependent on both the LED value and the switches. LED value takes a while to count up, so of course there's no output there. But let's assert a value to the switches. Right-click and select Force Constant. Let's change the radix to binary and set the switches to 0011. Running it again, we can see that if we expand the LED register, these 4 bits are assigned a value. We know from our code that the switches only work with the lower 4 bits, which makes sense. Now, while it's possible to test our entire designs by using this waveform editor method, it can get frustrating constantly forcing constants and having to readjust clocks and do all of these things. So instead, we're going to create a testbench. Testbenches allow us to create a module of HDL to test another module. This module is known as a device under test or unit under test. The testbench instantiates a device under test and ideally runs through all the possible inputs to determine possible outputs. The combination of these inputs and expected outputs are called test vectors. Before we write our testbench, we're going to close the simulation and create a new simulation set. Simulation sets in Vivado allow you to create simulations for different stages or components in the design. In a sense, you can think of each set as a different experiment. It's not a necessary step, but it does help to keep things organized. So we'll right-click and select Add or Create Simulation Sources. Then, in this drop-down, we'll select Create Simulation Set. I'm going to call mine TV_top, because we're going to create a testbench for the top level module. Then we'll create a file, and we can give it the same name. Click Finish. Remove this port and click OK. We can see that the default simulation set created by Vivado is still active, so we're going to set our new simulation set to be the active one. Right, so here's our testbench. We also need to set our testbench as the top module in the simulation set. There is, of course, documentation on writing effective testbenches, and I've linked to that in the description below. I've also included a link to some documentation that shows a lot of the features I've used in this testbench. There are other useful things you can do in a testbench, like printing to console or reading from and writing to a file, but for the sake of this video, we're going to keep it simple. Let's run through this code quickly. I've got a time and precision directive. I've also defined a module. You can see there's no inputs or outputs in this one. Everything is self-contained. I've created registers for input to the module we want to test, and wires for the outputs. Next, I've instantiated the module for testing. Now it's onto the details of our testbench. First, I have an initial block. These only run once. So we can put any initializations we want in this block, such as setting our switch values or placing an initial value for the clock. Then I have two always blocks, one for the clock and one for toggling the value on the switches. You can think of an always block as a thread. The reason for using two always blocks is that I'm using delays and I want a constant clock signal. If I toggled the clock and the switches in the same block, the clock would only toggle after 100 nanoseconds. So keep that in mind when designing testbenches. Right, let's go ahead and run this. If we scroll out here, we can see that immediately we have a clock signal. We can also see that the switch value is changing. If we expand out the LED signals, we can see the LEDs driven by the switches are changing. But what about the LEDs set by the counter? For that, let's create a breakpoint. Back in the board test module, we can see we've now got these red dots down the side of the editor. This allows us to set and remove breakpoints. If we set a breakpoint for when we first assign the LED value, and now go back and let it run, our code will stop when we hit the assignment. We can now see in our waveform editor that the value has been changed, though you will need to manipulate the waveforms bit and let the simulation run for a little bit longer so that you can see the outputs on the waveform. This is also a good chance to demo the step button, where we can go line by line and view the values of registers and wires as they're updated. So that's the basics for the waveform editor and testbenches. There are, of course, many more directives for testbenches. Here are some you might find useful. Feel free to pause and take notes. And that's all for this video. Thank you for watching. If you found this video informative, please leave a like and consider subscribing. If you have any questions, comments or criticisms, leave them in the comments down below. And I'll see you guys next time.